So I guess we can start, right? So
Okay.
Taha, you want to start?
Yeah, sure. So this week's topic is automated text summarization, and yeah, through some discussion with me, we thought that maybe we should include some like less topics and create some more space for discussion. So I'll just start by briefly summarizing what the topic is about and show some like first really old and simple methods to dive into the topic, and then Yigit and I will present like one of the two latest models that are being used now that we can call SOTA. And yeah, so the main idea is that you can come at any point and ask questions or discuss. So as presenters, we even have some questions for you that we had difficulty in understanding. So yeah, so let's just start. So what's a summary? So this is actually quite a controversial question, but I think this is the most convenient one that I happened to see online in one of the papers that I was reading. So they define a summary as a text that is produced from one or more texts that conveys important information in the original text or text, and that is no longer half of the original texts and usually significantly less than that. So this last part is the controversial part, and I don't know. So if you have again any idea, we can discuss more on that. So I think the length part would probably change according to the original document's length, but yeah, this is what most people accept as a summary. And yeah, summaries that it's already defined in the definition, but it may be produced from single or multiple documents. And it should preserve important information, and it should be short. So these are the main functionalities we're looking for a summary. And why do we need summaries is one other aspect. So the most important parts that I can come up with is, I think, so if, especially in our area, for employees and for student hunters, so-called student hunters, summarizing CVs is one crucial task that people are using. And yeah, summarization actually helps to share what we have learned. And so what we are doing in this reading group basically is based on that idea. We can call it a multiple document summarization in that sense. So, and also a single document summarization because we summarize individual papers read as well. And yeah, summaries also avoid wasting time reading something that doesn't contain what we are looking for. Yeah, we can use summaries in many ways. And so even my own research is based on text summarization, although I don't use it on normal structured text, but on dialogues. And yeah, summarization for dialogues, although it's another story, is also a new opening field, and we might as well talk about that later if anyone is interested. So again, yeah, go ahead.
I have a question here. Like BB said, summary should contain the important information, but there is no real definition for what an important information is. So I think that's the key point where like where the fuzzy parts start.
Yeah. So,
what are we trying to optimize?
Yeah, what I define as important information probably would be actually the part of a text that defines the rest the best, right? So we're basically, I think, trying to compress a document we have in hand in such a way that would lose the smallest bit of information in it. So yeah, we could actually define summarization as another way of compression, and we're just trying to basically compress a text data. Uh, yeah. So, but if anyone has any idea on how do we choose the important part in a text document, we can always discuss more. Yeah. If you have any more idea, just please go ahead and say.
So, do you guys have any input on that? What do you think is a good definition of a summary? Um, that's a really fundamental question. Okay, it differs from a lot of other research, but not like for some NLP research like machine translation, in the sense that the gold standard or what you're trying to chase is subjective, right? I mean, if you think about IR or e-commerce, there's a loss function, and your loss function is defined over some ground metrics that you're trying to get. Okay, so there's some ground truth. But here, your summary and another person's summary will differ, right? Just like in machine translation, like if you translate the sentence that I'm saying now into Chinese, if you have several different Chinese speakers, they'll translate it differently. So how do you get around that? Right? And so what counts as a good summary? What are your thoughts on that?
Covers most of the important topics in text.
Cover most important topics, right? So yeah, if we are going to say covers
Actually,
most
the most important topics can also change according to the context. It
Yeah.
changes. Yeah. It depends on what you're looking for as well.
Yeah, true. So actually, yeah, that's a good point. So for whom are we making the summaries is another aspect. So I think I don't quite remember, but I think one of the papers that I read on dialogue summarization was tackling that problem. So basically, we have some patient-doctor dialogues that are going on, and so the summaries we are trying to make have two aspects. Is it like, are you trying to do the summary for the doctor, which would be expected to be much more technical and like including many scientific terms, or are we making it for the patient, which would be expected to be much more simple in the language? So yeah, that's another aspect of doing a good summarization. And I think another like another aspect would be the scientific document summarization. Maybe Abhinav could make good points on that. So since like all of us are into research, we read a lot of papers and abstracts, right? So as me myself, I often realize abstracts that summarize the document itself, good and bad. So, but I'm not like, if you ask me, I cannot list your features, like features I'm looking for into an abstract. But in the background, I always aware that some of them are good and some of them are bad. So yeah, today what we want to explore in a way is what is that? So what kind of features makes a summary good, and how do we achieve automatization of that?
I think there is also another part of summarization, like how we said, like it depends upon the kind of documents that you have. I
Yeah.
think you can ask specifically some questions and derive a summary for that. It's called query focused summarization.
Yeah, yeah,
I think you just get a summary for the query you ask.
yeah, correct. Yeah,
And
true.
that might also be
Mhm.
good.
Okay, so you guys have hit on a couple important points, right? So the first one is like, okay, it's very much audience dependent. Like, who is the person using that summary, right? And if you know their task in doing that, then you can optimize for it,
Mhm.
right? So even the same person over different time spans will want a different type of summary. Like you guys are researchers, like Taha mentioned, like when you're reading the paper indicatively to try to determine whether that paper is relevant or not. For example, for this reading group, you might want certain information. Okay, when you want to read the paper to replicate it as a baseline, you want certain information. Okay, so that's also a little bit like query-based summarization. So Abhinav highlighted query-based. It's sort of like the lowest common denominator for saying something is sensitive to a topic, right? So you can say when Google search you a search result, okay, on the Google search engine result page, it is giving you a summary, and that summary is query focused because basically it shows you the keyword in context, right? It shows you your query and highlights the context to the left and the right of it in that. Okay. In the early days of search engines, what did they do? I mean, Yahoo and Alta Vista, probably much before your time, and Lycos also before your time. Also, these things gave summaries, but they were just the top N words of the document. Okay, just the first N words, non-trivial words of the document, and obviously that didn't really do a good job. So this is the idea between query-based and generic summarization. Okay? Generic summarization means just summarize the document. I have no particular audience in mind. Query-based means I'm here for a particular purpose. I have a query in mind, just like in the search engine, right? So that makes it quite different. Okay? There's another thing that Taha mentioned, which is like, what is the use of that summary? Okay, so you said, Yigit also said, should preserve important information, and he made the distinction. I think that's the key part, right? So what is counted as important? I mean, if I give you a longer summary, somehow I should be able to put more information in there, right? Okay, so if I give you a longer summary, great, I can fit more information. But what is the purpose of the summary? Is it supposed to help you support relevance judgments? Then I only just need to tell you that enough for you to make that decision, okay, to read the document or not, okay? Versus, so we would call that an indicative summary, okay? Just give me an indication of what's going on so I can support some type of task, okay? But there's also the idea of an informative summary. An informative summary is the idea that you encapsulate all of the important facts. You can throw away most of the rest of the document. So it serves as a surrogate or a proxy for the original document. Okay? So you don't want to read the whole press release or something. You only have time for 3 minutes. You get Google or Alexa or whatever to summarize the document for you, say it to you as you're on the MRT, and you never read the source document. That's called an informative summary, okay? Where you replace the document with the summary. And another thing that you guys also mentioned is abstracts, right? So abstracts in scientific document summarization, we know is a summary constructed by the individual, right? The authors of that document. And for that reason, we can think of the abstract as what the authors think is most important about the document, okay? Most important contextually from their point of view. But that's not really the summary of the document over time. You know that certain documents get cited more than others, right? So another way to summarize a scientific document, maybe Taha's going to go over that, is looking at the citations to that document, right? Like you guys have all read scientific papers, and those scientific papers, they have a related work section. In the related work, they cite somebody else's paper, and then they describe it, like X, Y, and Z 1990 did blah, blah, blah. Isn't that a great summary? Right? That's a one-sentence summary of somebody else's work in some type of context. Okay? So in that sense, an abstract is a poor summary because it shows the document only with respect to the time it was authored. Okay? If you think about the contextual summary that's evolving over time, as more and more people cite that work, they're all summarizing that document in some type of context. You look at all the citation sentences that are related to that document, then you have a very different idea of what a summary is, right? It's a use-inspired summary. Like, even though authors A, B, and C thought this part of their paper was useful, actually it turns out what they did was useless, okay? Nobody cited it for that reason. They cited it for some other reason, okay? And so that becomes what other people are thinking of it as the summary of that paper, okay? So these are all very good discussion parts to understand why summarization is different. It's very dependent. And so as Yigit said, if you don't know what you mean by important, what can you do? You're going to create what's called a generic summarization, which is just, I have no idea. Just give me the best you can do. Okay, but if you have some idea of the purpose, the workflow that the summary is involved in, can be much more personalized and can help a user much more. I mean, think about the very simple use case that you encounter every day in summarization. You do it every day. You use Google, you use Bing, or you use whatever, Baidu. You issue search queries. They give you summaries. Okay, could those summaries be any better than they are? Sure. I may be able to divine what you're trying to do. Okay, can give you a summary based on that. That's the whole idea of like the info box and other types of things in information retrieval that Google evolved over many years. They're trying to understand what you're doing and offer you a summary that's respected to that. Okay. So that's the summary of web pages. I mean, Google search is basically web page summarization.
Yeah. Okay. So,
Thank you so much.
uh, did you say something, Yigit, or?
I said thank you.
Oh, okay. Yeah, thank you. So, yeah, as we already mentioned, there are two types of generic summarizations regarding the number of source documents, just single and multiple document. Today, we will be mostly talking about single document part, but again, most of the approaches used there can be translated to multiple as well. And regarding the summarization method, there are extraction and abstraction-based summarizations. So basically, extraction-based summarization is the procedure of identifying important sections of the text and producing them verbatim, and using fusion, combine those extracted parts coherently. So most of the summarization systems that are used today are extraction-based, and that's because the abstraction-based summaries are not quite robust in terms of their performance. But the thing about extraction-based summaries is that they're not like the summaries that humans do. So as humans, when we do summarization, we usually use our own words and maybe use some novel and words that are out of the source document. But since it's quite hard to train models that would use words from their own vocabulary that are not in the source document, again, most of the systems that are used today are extraction-based. And the abstraction-based summarization, it just aims to produce important material in a new way. So basically, you're free to use new words that are out of source or even out of vocabulary. We will see a model that even uses out of vocabulary words. And yeah, so to give a generic comparison between these two methods is, as I already said, extractive directly chooses sentences and phrases from the original document. It is a one-to-one mapping with the original document, and basically uses three main steps: the intermediate representation, scoring the sentences, and then selecting the phrases and sentences. And it's generally faster, although it suffers from redundancy. So, oh yeah, so whereas the abstractive one it involves rewriting. The sentences might not map to a location in the original text, and the process is complex. So you need to both understand the language, the context, and then you also need to use generation, like generation of new sentences upon your understanding. And yeah, since it's a sequence-to-sequence process, it needs large data in scale. So yeah, hopefully you see the differences between these two systems. Yeah, now I'll just go through some earlier attempts at TS, which are like quite early. So this is actually the most cited paper on summarization, and it's in 1958. And yeah, when you see the idea, you will probably want to be a researcher in that time because it's quite basic. So what they do is they just so it consists of 6 basic steps. The first step is stem words to their root forms, and then delete stop words. And in the third step, you just compile a list of words sorted by decreasing frequency for each document. And then you find significance of each sentence. And the significance is just a reflection of the number of occurrences of significant words within a sentence. After that, you rank all the sentences according to their significance and select the top ranking sentences. So yeah, that's it. And so it's basically, there's not even, I think TF-IDF idea was not existent at that time. So yeah, you don't even do TF-IDF, you just, it's basically a count-based approach. And that was what summarization based on in 1950s. And again, we could probably say it's one of the first of its kind. So after that,
let me give you some background. So Lund was an IBM researcher. He was one of the first people who did natural language processing before it was called that.
okay.
And so it's basically like what Google or Facebook or other AI research institutes do now, which is like do cutting edge stuff. Because to do these 6 steps in 1958 by a computer is like like heresy. Okay, you couldn't do it. So you had to code this on punch cards and put it on mainframes. So this is the equivalent of like I don't know, 30 years of deep training or whatever that those crazy guys at OpenAI do to train their Dota agent. So this is really cutting edge at that time. Okay, so it's pioneering work. That said, I want to encourage all of you, even though it sounds like research at that time would have been very simple, okay? You are at the same place, okay? You can be doing cutting edge research now, which in 10 years, people will say, wow, you had it really easy as a PhD student. All the things that you do, are taken for granted now. I mean, to do your PhD research, it took you 4 years, would take me about 3 minutes of time in 2030, okay? That's what it's going to be like, okay? So just remember that you're always at the cusp of doing something great. And that's why a lot of people say, this is the best time to start up because there are always going to be new things that are going to be invented that are going to be worth billions. Yeah. So yeah, just remember that. Okay. It's always a good time to be doing novel things, except for coronavirus. Yeah.
Okay. So yeah, near the end of 1900s, there's again the naive bias. At least, of course, we use naive bias at every aspect in NLP. And yeah, you probably already are familiar with the general formula, but I'll just go through it again. So yeah, basically, as what we define as S here is a particular sentence, and the big S is just all of the sentences in the document, and we have hand-made features from F1 to Fk, and what we are trying to find in the end is whether a sentence is going to be existent in our summary based on our features or not. And how do we model this is by just through the generic formula. So and one aspect about naive bias is that it assumes the independence of features, right? This is one thing that we're going to discuss more in the following methods. You basically just go through all of the sentences and find their individual probabilities. And since the features are assumed to be independent, you just multiply all of the features conditioned on the sentence and then normalize it. So yeah, it was in 1995. Did you say something, Eve?
No.
Okay. It was used in 1995, and the features. I can say some stuff about that. The features were quite basic in the beginning. It was like, I think the position of the sentence was one feature, and then the length, of course, was one feature, and probably some count-based features like how many different words it includes, like compared to other sentences, etc. And yeah, I think it was like just a few features that they used. Yeah, I think it's quite clear. Do you have any questions on the slide, or should we just keep going?
So this harkens back to feature-based NLP before we had neural networks that could train and learn features on their own, right? So in standard machine learning that you might have been taught in your machine learning class, right? You basically have to engineer features that correlate with the class that you're trying to get. So what they noticed is, of course, that if you have very short sentences, they're probably not going to be in your summary. Conversely, if you have very, very long sentences, they're also probably not going to be in your summary, okay, because they take up too much space, right? If it's at the beginning of the paragraph or at the beginning of an article, that's a good sign that it might be important, right? So all of these things are parts of the features, if you will, that people thought were generic enough to put in the summarization system for general text.
Yeah. And one thing that was interesting in this paper was they also figured out that not only the position of the sentence in the whole document, but its position in the paragraph is also important, because they realized that most of the sentences that are at the end or at the start of a paragraph are actually quite good candidates for the summary. So other than the position in the document, they also set a feature where it indicates the position in the paragraph itself.
Yeah, so you can think about this. This goes back to the discussion we had last week about semantic analysis and RST. Right? RST says, I have a document and it makes some types of tree structure. The tree structure being having a satellite and a nucleus, right? And so in English and in other languages that have devised some type of text structure, right? We have this idea of a paragraph saying that whatever sentences in this group are somehow contiguous and form an independent block from each other. So that we have groups of sentences as paragraphs, right? Yeah, but again, this is sort of like the simplest way of having a linear set of symbols to represent language, right? But many times in discourse, you actually want to have a tree-like structure, right? You make some points and then you come back to another higher order points and you come back. And so that type of semantic analysis can play a role in summarization too. Okay, so this idea of doing position, as was marked by Taha's cursor here, using paragraph and sentence, is just sort of like the poor man's version of semantic analysis that Ting and Jachi were talking about last week. Okay, so if we had an RST analysis, we could use that for summarization.
Okay, so following this research, at the beginning of 2000s, Osborne claims that most of the existing approaches always assumes feature independence, like in naive Bayes case, but they think it's not correct. So they use a log linear model to kind of obviate this assumption, and they show that empirically the system produces better extracts than the naive Bayes model. Yeah, I just included the formula, but it's the basic idea is that they assume feature independence and start to get better results. And then comes the hidden markov models. So again, this is based on the idea that all previous models were feature-based and also non-sequential. So yeah, Conroy and O'Leary, so they thought the summary-based system should be sequential, and they modeled the whole problem in Markov models, hidden Markov models. And so what they did was quite simple in the sense, but again, yeah, it was in 2000s. So for each sentence, their model has 2s plus 1 states, and S here denotes the number of summary states. and S1 is non-summary states. So basically, if you just take a look at the figure, what their model does is they feed in each sentence one by one, and at each point the model decides if that sentence is going to be a summary sentence or not. And so the number of summary sentences are predefined. So in this case, we have only 3 summary sentences. And if a sentence is decided as a summary, it just goes to the next summary state. And if not, it stays in the non-summary state. So yeah, it's quite simple, but then what this model brings novel is that if you probably know how hidden Markov models work, but so when you're in a state, you don't know about your previous states, right? So what this state, how this state is different from the previous one is that they are coming from a state where the previous sentence was summary. So what it changes is that if your previous sentence was a summary, then the next sentence in the document has a higher probability of being a summary sentence. So in a way, they bring sequentiality in the model. And yeah, after this, we directly jump into the neural part because we are limited in time. So yeah, I think it's 2017. Yeah. So this is one of the state-of-the-art models that was introduced 2 years ago. It's called pointer generator networks, and the idea is mostly based on attention. And it goes like this. You have here in the red part an encoder that basically encodes your source text, and also you have a decoder that just decodes the summary part. And after you decode each token, let's say in the case of this example, you just encode your whole source text and you decode one summary word. You also find all of the attention of the source text according to this decoded word. So like you find attention of all source text according to Germany here. And then you just combine this attention with the hidden states here to a context vector. And combining your context vector with the decoder, I'll just explain how they do that. You find a vocabulary distribution, right? And this distribution is actually not only on the source words, but on your whole vocabulary distribution. So like let's say you have a predefined vocabulary in the end and at the background, and you find your source text attention. You don't need to produce or decode a word that is only in the source text. You can as well decode some word that is only in your vocabulary. So yeah, this part is kind of important. So if you have any questions, you can go over them, or any like confusions. If not, I'll just keep showing how they do the network part.
You guys have any questions about how the decoder is being used? You know, this yellow part.
There be like translation, like starts from one word and then goes to decoding, makes a new word, then fits a new word again and again and again.
Yeah, so it's a recursive decoding process, but it's based on just the encoded version of the entire text that's going to be summarized. Right. So it's very similar to the neural translation method.
Yeah,
right?
and it's the baseline they introduced, so they'll have their own novelty in the next slides.
So this is different from sequence of attention.
I don't think it is. So does that also have the vocabulary distribution like in MT?
I don't think so.
Oh, they don't. Then maybe that's the different point. So,
What is this vocabulary distribution?
okay, is that so? What vocabulary distribution is? So from vocabulary distribution, we choose a word to decode next, right? So we're basically choosing our summary words from our vocabulary distribution. We just sample words, and in order to find the vocabulary distribution, we just do it through our attention from our source text and the, the the hidden state of our decoding. So like we just don't use the words that are in the source text to create the summary, but we are using our own vocabulary.
Oh.
Yeah, you see. So that's the part that makes it kind of abstractive. So yeah. So for example, let's say here is like win has a quite big attention, right? So in our vocabulary distribution, win and beat is quite similar, but we don't need to use just win. We have our own vocabulary, and beat got like more attention in the vocabulary. So our next word in the decoder might be beat. So it will go like Germany beat, and then we will do this whole thing again and find the next word in the sum.
Taha,
Yes, go ahead.
isn't that vocabulary distribution is the context vector itself?
Actually, the context vector is just attention, like a combination of attention and encoder hidden states. And to find our vocabulary distribution, we just have an internal mechanism that combines context vector with the hidden decoder state and find this distribution. So it's actually
Oh,
different.
okay.
Yeah,
Okay.
different from the context vector. I think I'll have more slides on that if I'm not mistaken. So it will probably be more clear after some slides.
So actually, it seems like for NMT, you would also have your own vocabulary.
Yeah, I think this whole thing would also work for NMT because it's again sequence to sequence. Yeah, and so this actually just the baseline in the thing. Yeah,
So what is it called? Code generator. What is it?
yeah. This
That's
part
next.
this part yeah that's nice.
Oh.
So this part is just the baseline. They built their own pointer generator thing on this baseline.
So let's make it clear. ABC's work. This is the work by Chris Manning and his student at Stanford. They're just using a simple attention sequence to sequence attention model as their baseline.
Mhm.
So that's what Taha's describing now. It's not
No wonder
pointer
it looks
networks yet.
Yeah.
It's our basic neural model that I think most of you know with.
Yeah. So just to show some content from the paper, so how they compute the attention is quite standard. So they just have a combination of the hidden states from the encoder, and ST is just I think the decoder hidden state, just one hidden state, and some bias term. So they just combine these linearly and take a softmax in the end, and they have their attention distribution in the end. And this attention distribution right here is combined with the encoder hidden states to find the context vector. And so they basically just find a weight sum of all the encoder hidden states according to attention. Find the encoder hidden state.
Now, you guys, please remember that this work is pre-transformer. Okay, so in the transformer model, we have the key and the value, right, and the query. So it can be done differently than this model. This is before the transformer network was created.
Yeah. So yeah, I think this is the part that Yigit was asking about, the vocabulary distribution. So how we find vocabulary distribution is we basically have two linear layers that combine the encoder state and the decoder state. Also the context vector and decoder state. We just, as I just said, we just take them through two linear layers, and then apply a softmax to find the final vocabulary distribution. And after we got our vocabulary distribution, the only thing we need to do is sample some words from it for our next word in the summary. So yeah, I actually have some question that I want to ask to you. I wasn't quite sure when I was reading the paper. So we just discussed the summary is actually shorter than the passage, right? Then the decoder should not create a token at each time step because it's basically shorter than the source document. But I don't think they explain how is that handled. So like I don't know, maybe the decoder just for some time steps it just doesn't create a word and just decode some particular token that means maybe pass or something like that. But yeah, they don't explain it, so it's just my take on the question. But yeah, if anyone knows,
So did they stop when it produces the end of sentence too? Right? I think the end can
Yeah, I
they
think,
stop and
yeah, I think when the stop is based on the decoder itself. When the decoder decodes a special token, usually it is called the end of sequence, and the coding process will end.
yeah, okay, but my so what I don't understand is so maybe there is some important part. Oh, okay, so then it goes on until it creates the end of token, and it's
Yeah.
there's no like terms between, right?
Yeah, right.
Oh, I see.
And how, about how to make sure that the summary is shorter than the context. I think it is for the sequence model. It's just because of the training data.
Yeah,
Yeah.
data, yeah, correct. Okay, I see.
Yeah, so I think yeah, means analysis is exactly right. It's based on the training probability that it generates the end of summary token, and then basically you stop decoding there.
Mm.
Just like in the NMT case, right?
Yeah,
when you're doing
yeah.
that translation.
So how do they ensure the vocabulary is different from the
I think it's they have it. Yeah, they have the database. It's like predefined from
oh, okay. So they had the vocabulary.
yeah. So maybe they use I don't know WordNet, like some other corpus to define the vocabulary.
no, if I'm not wrong, then you have the vocabulary from the data itself. You
Oh,
restrict
but it's not documented. Like it's they just have the vocabulary from all other documents.
Yeah.
Okay. Yeah, it makes sense as well.
yeah.
Also, when you're summarizing one document, use vocabulary of other.
Of other documents as well. Yeah.
I mean, you have the entire embedding, right? So,
Yeah.
I mean, at this point, when have you made this word glove embeddings are already being used?
Yeah.
So it could be that you just predict the word from any glove.
Oh, okay. So,
Yeah.
so it's not like you actually have custom vocabulary.
No, I don't think
But
it's
I
a
think it
custom
should
vocabulary.
still work if you have the embeddings, right? Like even if you have vocabulary from different corpus, still
Yeah,
yeah.
not a problem. Yeah. I mean, the important point is when you say it's abstractive, it's just not choosing only the words that are in the document.
Yes, correct.
But even in this type of representation in the baseline, those words are being represented by a vector, right?
Mm.
And embedding. And the embedding is sort of it's not a one-hot vector, right? It's basically, well, an embedding sort of incorporates other contextual information. Yeah.
So yeah, then here comes the part they introduced, and so you can see them on the network as the yellow parts, apart from the decoder that was already there. And so what they call this is the generation probability, pgen. And what it does is for time step t, it's used to introduce a soft switch to choose between generating a word from the vocabulary or copying a word from the input sequence itself. Yeah, so basically looking at your context vector and the decoder hidden state, you decide if you want to create a new token from your vocabulary or just choose one word from the source text. So they're just doing a linear combination of the context vector here and the decoder state and the input itself to find the generation probability. And then the final distribution just becomes, so you either choose to generate a new word and you use the distribution from the previous steps to find a new word, or you just choose a word from the source document and you use your attention distribution to choose. Yeah, so this part actually brings the ability to produce out of vocabulary words. And yeah, the authors claim it's the primary advantage of the pointer generator models. There is actually one more thing they introduce in the paper, and that's called the coverage mechanism. So one thing that's quite common with sequence-to-sequence models is the repetition problem. And the solution to this is the coverage model that was introduced by Tu in 2016. The main idea is like in 3 steps. You first maintain a coverage vector, CT, which is the sum of attention distributions over all previous decoder time steps. So basically you are compressing all previous distributions into some vector. And then at each time step, the coverage vector is used as an input to the attention mechanism. So this term here is what introduced for the new case. And what it does is it ensures that your attention mechanism is now aware of the previous attention mechanisms. And in that way, it tries to avoid creating the words that was already repeated before. So yeah, this is another mechanism they introduce in the paper, and it helps to reduce the repetitions in the paper, repetitions in the summary. And they also have done an experiment with the baseline and the model they introduced, and I thought it was quite interesting, so that's why I included them in the slides. So it's kind of confusing, so I'll just first define these 2 things. So by out of vocabulary words, what we mean is words in the source document, but not in the vocabulary. So yeah, so basically our model is not aware of them because they are not in the vocabulary, but we have seen them in the source document. And by novel n-gram, what we mean is n-grams that actually don't appear in the source text. Okay, so our best model, the pointer generator model, is abstractive because it is able to produce all of vocabulary words that are not in the source document. But it's not actually better for producing novel n-grams than our baseline. So this is actually quite interesting. So it is kind of more, I would say, not open to like, how do you say, controversial probably. Yeah, it's quite controversial in terms of n-grams, although it can produce out of vocabulary words. And yeah, compared to our best model, the baseline model actually doesn't produce out of vocabulary words, but it produces more novel n-grams, especially for like lower n-grams. Yeah, this was one experimentation they did in the paper. And honestly, I don't have much interpretation why, but if you do, we can go ahead and discuss.
So how come it's abstractive, but it produces words in the source but not in the vocabulary? Isn't
No.
it extractive?
So the OV words is words in out of vocabulary. You know, so it's out of vocabulary.
So how, if it's out of vocabulary, how come it can produce it? Because it's abstractive, right? It's not extractive.
No, the thing is, the extractive part is when you take your words from the source.
Mm.
But yeah, if you're using words that are not in the source, then you're abstractive.
So these two are contradictory.
Oh yeah, you're right. Okay, maybe the OOV words per definition
The
is
OOV words are words that appear in the target vocab are not there in the source. So, but they somehow appear in the target vocabulary. So you don't have a good representation for them. So that's why they copy the sentence words from the source sentence.
Hmm.
So you just build a vocabulary over the entire corpus, and then you don't find some words in the target for the abstractive sentence, the target sentence. Let's call it the target sentence. So you would want to copy it from the source sentence. That's what the pointer generator network does. So this usually happens even in machine translation. They say we will take only 3,000 words for the French sentence that we are decoding to. So some of the words get the unknown token. You don't know how to produce them. So you copy the words from, depending upon the information, attentional information from the source sentence. But yeah, but for it to be abstractive, it has to produce new words.
Yeah, like
Yeah.
so this sentence I took from the paper itself, but I was quite confused as well. Yeah, I'm not sure if
Novel
if it's
engrams.
the
These engrams don't appear in the source
So-
sentence, but
so-
get produced in the target sentence.
So in the third point, it should be produces novel engrams, not OOV words, right?
This novel is abstractive.
Isn't it? So what's
no
the
null
other-
engrams is actually also done by the baseline itself.
What is the best model? Oh,
The best model is the PG, so like pointer
Pointer
generator,
generator.
what they introduced.
but does not produce many novel engrams. It should be the other way around.
I
Produces
think it
novel
was this
engrams.
way. We can check the paper again, but
Yeah, I think
Maybe they were
this
confused themselves.
the notation on the slide about what OOV means is a little different than what we standardly mean. So in Taha's slide, what he's counting as out of vocabulary means it's not in the general vocabulary of the language
yeah,
model,
so
but
basically
occurs
not
in the
here.
source document.
Yeah.
Okay, so that would be extractive.
Yeah,
Okay?
I think so.
Yeah, but usually when we think about OOV, it means not in the vocabulary itself, which would be abstracted, like dreaming up a word. Like that.
Not
Okay,
yeah,
so
so not in vocabulary.
yeah, so it's I think Taha's terminology is a little okay. So what he means by out of vocabulary, I was also trying to puzzle this out. Okay, is that OOV like say like today? Let's say there's a word about like I don't know, even newer coronavirus. Okay, novel coronavirus. Okay, so that would be an OOV word because you've never heard of it until I said it. Okay, it's not in the general language model. Okay, but it appears in the source text that you're summarizing. Okay, so that is what Taha means by out of vocabulary. It doesn't appear in the language model, but it appears in the source text.
Yeah, so I think basically what they if it happened with the baseline, I would not be able to use that word because I'm only taking words from my own vocabulary distribution, right? But then with the model they introduce, now I can as well choose to get that word from the sentence itself. So that's why they are saying it's
So isn't it
in a way
extractive?
yeah, I feel like it combines both abstractive and extractive.
Yeah.
Yes,
But-
it does. So if you go back a couple slides, I'd like you guys to all think about what that means. Okay, like yeah, here, all right, or the one with the equation. Both are fine. Yeah, okay. So you've got two lines here, right? You've got this one over here, and you've got this one over here. Okay, which one is the extractive part? You guys want to take a vote? Red or green?
Green.
Green is the extractive, right? Yeah, because it's basically I put attention on words that are already in the text, right? Red says, I don't know, just give me what's going on and then I'll predict the word for you out of thin air, like pluck it out of the distribution. Okay, that's the abstractive approach, right? So it's both. Their novelty is to introduce this this switch, right? The switch which does you know, what's the probability? right? To switch between our extractive and our abstractive, right? So you can do both.
Mm.
You can have your cake and eat it too. Just put a switch, right? Okay. So that's what they mean by at that. So usually when we say OOV, we mean this part. Okay. But in the case that Taha is using on this slide, he means this part.
Mm.
Okay. So
Yeah.
it's a little
So
bit
actually,
different.
that explanation part is just in the paper is just under that figure. So maybe scribes could make it clear by checking that part and doing the explanation.
So how does it do the switch? Is it like more than
That's so this we actually learn as well right here.
uh,
Yeah, and like so basically, if you just look here, we decide to choose a new word or not by just doing a linear combination of the decoder state and the context vector.
oh, because it's a sigmoid. So
Yeah,
this
sigmoid.
washes it to
Right.
either 0 or 1.
Yeah, so in Slack, you will see a picture from the original paper, which basically complies with Taha's understanding of OOV. Okay, it says the models that are abstractive struggle with OOV. Okay, meaning that the language model, even though it can dream up words, it won't be able to dream up words that are occurring in the source document, have not been seen before. So like again, if I say novel coronavirus in some text article, the language model has never seen it. It's out of vocabulary for the language model, but it's present in the source text. Okay. So they're basically saying OOV is something that you can extract from this rather than abstract and dream of it from the language model. Okay.
So actually this picture isn't really accurate because it's not actually combined between the two distributions.
Yeah, I think so. I think this is just this part, like the attention part. Yeah, you're right.
Because it looks like it's kind of adding the distributions together. So you're kind of assuming that the two vocabularies are the same.
Yeah, I think actually
No, but the
the
formula agrees with this picture, this final distribution picture, right? Because the final distribution has both the blue distribution from the attention distribution as well as the green distribution that comes from the vocabulary.
well, I think it only has the blue part, right?
That part that your cursor is
Oh,
on
yeah,
is
sorry
on
about
the
that.
blue part. Then
Yeah.
it has the green part, which is the P gen times P vocabulary, but they're added together, right? So that's
Yeah,
why
but
it's stacked
this
on
part
top
is
of each
actually
other.
already this already includes the blue part.
I don't think so. They're just saying
Because-
that you use the context vector to decode the probability distribution for the vocabulary, right? It's not that you're adding these or concatenating them together. You use the context vector plus the previous word beat here to determine the vocabulary distribution, which is your green distribution. But then you add the two together, right? Which is that final distribution that you
Oh, I
have,
see. Okay. Yeah.
right? So the plus sign here on the bottom of equation, in the middle of equation 9, is equivalent to stacking the green and the blue bars together
Yeah.
on that slide.
But they don't normalize. Very strange.
Yeah, I don't think they normalize.
Then how is it a distribution now? How do they pick the next one?
Well, you could still normalize it afterwards and do a distribution, right? So maybe at this point you haven't normalized it yet,
Yeah,
right?
sure.
Because this is just adding it together. This is just saying I have a switch. The switch goes from between 0 and 1. So I can either make it entirely abstractive, right? And just use the language model to predict everything, or entirely extractive and use the attention over the source words to determine what to say, right? That's all this pgen and 1 minus pgen is saying. But it doesn't mean that these two things add up to 1, right? It's not a distribution.
But they're using it somewhere.
Yeah, I mean, then you could put it through a sigmoid or whatever later, maybe not on this slide, but somewhere else, and then make it into a distribution to pick from, right? You
So
do
these
the
are just
softmax.
the logics.
Yeah.
Maybe they pass it through the softmax.
Yeah, maybe
Yeah.
they. I might have not included them. Yeah. Yeah, so just some examples that they thought was good in the paper. So yeah, they put these to just show the out of summary words. I mean the out of vocabulary words that the system is able to produce. So the articles goes as smugglers lure Arab and African migrants by offering discounts to get onto overcrowded ships if people bring more potential passengers, a CNN investigation has revealed. And the summary is able to like create both under like out of vocabulary and like new engrams in that sense. So it goes like CNN investigation uncovers the business inside a human smuggling ring. So yeah, it's quite successful. Although, but like they only include 2 examples in the paper, so it's probably yeah.
Yeah, this is figure 5 from their paper.
Yeah, this
so
should
they,
be
they
novel
say these are
summary.
novel
Yeah,
novel words. That means these are the words that came from the language model.
Yes, true.
The green part of the distribution in the previous slides.
Yeah, and this again should be novel summary words, and this goes as eyewitness video showing white North Charleston police officer Michael Slager shooting to death an unarmed black man has exposed the discrepancies in reports of the first officers on the scene. So the summary now is able to produce, despite more questions than answers emerge. It seems like, yeah, quite handcrafted, but it's quite successful as well in controversial SC police shooting. Yeah, these are 2 examples they include in the paper. What's that?
What's SC?
I think it's
South Carolina. I think Charleston is a city in South Carolina.
Wow, how does it know?
how does it know? I wasn't even aware of that.
I'll check. And let's see how good the neural networks question answering geographic question answering. I don't think I've been to Charleston myself. Yeah, it's a city in South Carolina.
Maybe it says.
And it has 6 possible coronavirus cases. Yeah. what came up.
Yeah, okay. So this was all about the PG networks. Now I'll let Yigit continue on another approach, and yeah, we will probably go. We'll probably have more controversy on this one, so yeah, we can exchange anytime. So yeah, Yigit, you're there, right?
Yeah. Thanks.
Okay, you can take the hand.
This slide, I think it should be after the comparison slide, as you remember, the abstractive and extract methods. Yeah, but it's okay. It's there about the same paper. It's okay. We can continue.
You can, if you want, you can take the share.
I think everyone already knows better than me. Yeah, so it's fine.
Okay, just it's okay. We can.
Why don't you stop your screen share and let Yigit share? Because Yigit, you're also on the document. So just find the green
I'm using my phone. Can we continue from there?
Okay.
Oh, okay.
I'm not on the PC.
All right.
Nah.
So you have to tell Taha to forward the slides.
Okay, I can do that.
Yeah, thanks.
Of course.
The next paper is called Fast Abstractive Summarization with Reinforced Selected Sentence Rewriting. It's actually a hybrid approach that combines these 2 approaches. It actually has 2 main parts, which is the extractor agent and the abstractor agent, where the extractor agent selects and highlights the important sentences, while the abstractor network rewrites that. And I think that there's this interesting thing called actor-critic policy gradient, which they used for sentence-level metric rewards, because because when the abstractor generates some sentence, there's no real differentiable way to compare the result with the ground truth. So we use some other network to calculate our value function so that the policy is updated according to the estimation coming from that other network. Can we continue?
Yeah, of course.
Yeah. So we have the policy model and the value function, where the value function is we have it's mapping policy variables to the value. So critic is learning that function so that we can update our policy variables better the next time. I think this looks a lot like adversarial networks, but it's not adversarial, but one of them is helping the other. And I think this is more art than science, because both have initially different learning rates, and I think they have to change adaptively in the long run, because if the critique learns it very quickly, then it's going to produce gradients that would not be very helpful, because we are at the beginning of the training. Anyway, we'll see where this is used. Okay, so the model is, as I said, it has two parts. I think this is a redundant slide, which can be removed with an summarization model. Can we continue?
Yeah, sure.
Okay. Where are we? Oh, okay. The novel thing in this paper is that they, in the extraction agent, they exploit word sentence hierarchy. So they take word embeddings inside the sentence, and they process it sentence by sentence, but not all of them. So the next important thing is it also has to capture the longer range relationships between the sentences. So they also use obviously some LSTM and bidirectional LSTM and RNN, and some other LSTM RNN, which we didn't understand how they work, because we'll see in the next slide. Can we go?
Yeah.
To the next one? Yeah. Here, all the arrows, like they look like they're circular.
What did you say? I'm sorry, we didn't catch that.
in this, this is the extractor agent, and all of the data flow at some point it turns to the beginning.
Yeah, so
We didn't understand this part.
yeah, so basically maybe we can first try to explain what we did understand.
Yeah,
And
maybe. Okay.
so that is, yeah. So basically, there's one convolutional part which does individual sentence encoding from the source document, and it basically gives an encoding for each of the sentence in the source document that we call R1 through R4, right? So for the sake of this example, just think we have 4 sentences in our source documents, and now we have sentence encoding for each of them. Then we feed these into a BILSTM to get a context-aware sentence representation, which we call H0. So you can think of this blue part as the encoder, and the green part as the decoder. So after you get your context-aware sentence representation, you just feed it to the decoder to get a summary sentence. So this LSTM, what this LSTM does is, oh, what's happening? Okay, what this LSTM does is basically is choosing a sentence at each iteration. It that will be included in the summary. But so what we are not clear with is that this LSTM's, the decoder's output is also being fed to the BILSTM back to create the next context-aware representation. So it might be some vector that that is aware of both the document context and the summary context, but it's not clearly mentioned in the paper. So if anyone is maybe aware of the paper or has some idea, could join the discussion.
Okay, from my reading of it,
Okay.
and I will put the caption of the original figure
Mhm.
into Slack so that you can follow. Just to show you the right place. Okay. Like Taha said already, you have your standard word embeddings, and you get a sentence representation for each of those, right?
Mhm.
So this is our standard sentence or plot vector embedding, right? And then you pass it through a BIOS-TM, and you're going to produce, as Taha said, at each time step, a particular sentence representation that represents one of the sentences, okay, not all of them. So for
Oh,
example,
okay.
this H0 represents R1 because the attention is focused on the first
Oh,
sentence.
nice.
Okay, that represents
Didn't
this
get-
dotted arrow over here. Okay, so this dotted arrow is saying, okay, the previous sentence that was extracted was H0, right? So a previous sentence extracted was H0. So at the next time step, at time step H1, I'm going to take that sentence. Okay, sorry. I'm on the research as well. Okay, I'm going to take that sentence, okay, which I extracted and made at H0, feed it into the LSTM, along with the attention over all the sentences in the blue, and create H1. Okay, H1 is actually an encoding of R4, right? Because you can see in the third time step, the maximum attention was placed on the fourth sentence, right? So at the third time step, when I'm producing H4, right, I'm going to do it by selecting that sentence, right, and passing it here. Okay, so that's how you get this sequence 0, 1, and 4 is because of the attention that's passed on here, right? This is index 0, this is index 1, and this is index 4. Okay?
Also, the blue arrow is actually attention itself.
Yeah, it's basically
Oh.
saying which one was most attended to. So that was
I
the
see.
sentence that was picked for the summary, right? So this summary reads H0, which is the first sentence, R1, right? Then the next sentence that was picked was H1, right? Okay, H0 was not this sentence, sorry. Let me redo this, okay? So H0, I don't know where H0 came from. It came from
Yeah.
somewhere, okay? But then after you produce the first sentence, you pick the second sentence based on the context-aware representation of that first sentence you picked, okay? So that means you went ahead and said, oh, out of all of these four sentences, the one that looks best to present on top of H0 is sentence 1, right? Because the attention is here,
And
okay?
does these parts like define anything? Because so every part they choose, the arrow just disappears, right?
Yes, that's
So-
right. You can't pick a sentence that you've already picked,
Oh, that's what it means.
right? If you put H1 in there, you're not going to repeat it. That's coverage, right? So you're not going to be able to select it. So that's why in the next step here, this one over here, this is H4, right? That says after you decided to pick H1. So my summary right now is H0 and H1 because at that time step, right, I've already picked H1, okay? So I've already included it, right? And so I want to pick the next sentence. The next sentence says, I'm going to use H1's representation to attend to all of the blue sentences that I have available, right? So I only have as available R2, R3, or R4 to pick, right? So which one am I going to pick? Well, from the attention, it looks like I'm going to pick R4, right? But I'm going to create a context-aware sentence representation of it called H4, okay? And H4 is going to allow me to pick the next sentence after that, right? Okay, so which sentence am I going to pick next? Can you guys guess? It's going to pick R2, right? So I'm going to write something like H2 here. Okay, that would be the next step because basically I've thrown away the possibility of extracting R1 again. I can't select R4, and so I only have to pick between R2 and R3. Right? Everyone get it?
I have a question here. So
Yeah.
actually, this model is just a point network.
Yes.
Yes, but a little difference because in the point network, it is usually used for like sentence ranking. So the decoder will generate the length of the sentences generated by the decoder should be the same with the encoder. But in this case, because this is summarization, we only pick a subset of the encoded sentence. So if we do this decoding step, how can we stop it? I mean,
I also have the same question. So I think about, I guess, probably, for example, in the second one, you generate by decoder, probably there is a stop signal. And
yeah, but
then you stop it.
actually in the implementation of point network, in each step of the decoder, you just compute the attention distribution over the encoded sentence and pick the one that has the highest attention as the next sentence. But how
I think here you stop after you pick up the number of sentences. That's how extractive works. Right? So you say I want to produce a summary of 50 words, and once you produce 50 words, you stop.
so hard constraint.
Yeah.
So basically, this is just one part of the system, right? This is actually a reinforcement learning system, and what they do in the whole model is they take the extracted sentences and then take it through some abstractive model and create the sentences.
Right.
And what they do to get the stop thing to the model is when they train for the ground truth, they have some number of sentences, right? And whenever the system went above the number of sentences, like comparing to ground truth, they just penalize the system. and if it's under the number of sentences, they reward it for every new sentence that the system generates. So it's basically learned through the model.
Yeah,
in that way.
I know. I know in their policy gradients, they will penalize the summary which is too long. Yeah, but and use this reward to update the parameters in this model. But I mean, what is the mechanism to stop the decoding?
I think I have it somewhere. Yeah, so this part is explaining it's a part of the paper.
Yeah.
So yeah, you already said it's some kind of problem, and how they produce a solution in the article is they add a stop action in the policy state. So it's basically an action in the action space. And as I already said, whenever so in the training data, they have like grand truth sentences, and so for the grand truth, whenever the number of sentences is enough for the enough, the model produces a stop action, right? So the model is basically learning to produce this stop action. Yeah.
So those of you who are keen in reinforcement learning will know this is the actor critic algorithm, right? So it's learning to predict the value function to decide what action to take. And like Taha just said, when we're talking about how to decide.
I still couldn't understand how the extraction probabilities are used.
How the extraction what?
Probabilities.
Oh, how the extraction, how the system decides when to stop extracting, or how to determine which sentence to extract given that you have to make an extraction.
No, you see that extraction probabilities thing, right? I'm still trying to understand its function there, because that's the thing that is learned with the reinforcement learning part.
Right. Yeah. So on the paper, on slide, I can't even tell. It's page 678 of the original paper. Yeah, they're using the vanilla policy gradient algorithm to decide which sentence to extract, right? And it's based on this idea of the advantage function, which is a standard thing that you would learn in reinforcement learning, right? That you want to extract a sentence when it's better than an average sentence to extract, right? That's what we mean by advantage, right? So how do you compute that advantage is based on whatever the loss function is, right? So you have a computation of what sentence is good to extract from based on the training data. I don't think that really answers your question, though.
Anyway, okay. Thank you.
So there are two parts of this. One is you're trying to extract the sentence, but then after extracting, you have to abstract the sentence, right? This is the post-editing part. So you're basically saying which sentence do I want to take as source material? Okay, that's the extraction step. And then how am I going to edit that sentence so that it's locally contextually good, which is the editing, the abstractive part, right? And then the policy gradient from the actor critic is basically saying, okay, now that you did all of those things, was that a good sentence to pick? And did you apply the right abstraction procedure to do it, right? And if I did that well, then I get a reward. If I didn't do that well, then I would get penalized, right? And if the reward and penalty system is good, then over time it will learn which things to extract and which edits to make to the sentence, right?
So in this case, both agents get penalized or just one?
I'm also trying to figure that out.
I think, yeah, so this is the part where the whole model is seen. So I feel like
Yeah, train full model and that's last night. RL is applied to train the full model and
so. What they're doing is basically their first before starting the reinforcement learning part, they first train the extractor and abstractor separately. And only then to fine-tune both models together, they start the reinforcement learning part. So maybe the abstractor is not even rewarded in the
Abstractor has nothing to do with the RL.
yeah. So yeah, we only then fine-tune the extractor in the RL part, and abstractor is just pre-trained basically.
Oh, okay.
So how do you train the abstractor?
You have like separate data for that. But it yeah, it's explainable. Do you want to continue it or from here? I guess.
Where are we? Okay, we can skip here because we already discussed.
Okay.
Yeah.
Yeah. True.
So here is the summary of the training. Reward function is, I think, the critique part of the RL, which tries to compare generated sentence and the summary sentence, and it tries to learn a value function, and according to that value function, the policy gets updated, which is how the extractor chooses which sentence to extract. So this is, I think this is all about this slide.
Okay, so on the abstractor, you actually have to go to the supplemental notes to understand. So I copied it into Slack. So if you open it up, there's on the first page, it gives you detail about how the abstractor works. The abstractor is basically a copy of C's model that we just learned. Okay, it's basically, as it says there in the paper, it's sequence attention sequence model. So it's very much similar to the paper we just looked at to do abstractive summarization. Basically, you can either copy or you can hallucinate new words using the abstraction. Okay. And so we use that to do the abstraction process. Okay.
Okay.
Should I keep going?
Yeah. Can you continue from here, because
Okay.
this,
Sure.
yeah.
So yeah, yeah, as you already just said, the solution to this. Oh yeah, so one thing I want to stay on is that when you start the extractor and abstractor thing just from scratch in the RL, it doesn't work quite well, because when they are randomly initialized, the extractor will often select sentences that are not relevant. And if that's the case, then it would be quite difficult for the abstractor to learn to abstractively rewrite. And in result of that, without a well-trained abstractor, the extractor would get noise reward. So in the end, the system fails. And the solution to this is the thing we just discussed, by optimizing each submodule separately using a maximum likelihood. So what you do is you first train the extractor to select salient sentences, then train the abstractor to generate shortened summary, and finally use RL to train the full model, right? So how does the extractor training work is you just do sentence selection, formalized as classification. But the thing is, most of the summarization data sets are end-to-end, right? So it's document summary pairs. So the solution to this is you provide a proxy target label for the extractor. And to do that, you just take a ground truth summary sentence with the given paragraph. And by using a metric called Vuge, you just choose the sentence that is most similar to the ground truth summary. So now you have a training data for your extractor, where basically you have a document and sentences that that are candidate for extraction. And after you have this, in order to create data for the abstractive part, you just create training pairs by taking each summary sentence, that is the ground truth summary sentence, and pair it with the extracted document sentence. So this is what you're trying to achieve with Abstractor anyways. You're trying to get an extracted document sentence and make it into a summary sentence. Then you just train as usual sequence-to-sequence model to minimize the cross-entropy loss. Yeah, and in the end, you just do the reinforced guided extraction. To make the extractor an IL agent, they just formulate a Markov decision process, and at each extraction step, the agent observes the current state, which is the document and the chosen the summary word chosen in the previous step, and samples a new action. So again, the action we will speak about it in the next slide again, but the action could be the stop action as well, as we just discussed. Yeah, in the end, it extracts a document sentence and receives a reward. So yes, the paper, in order to make the extraction stop at some point, they add a stop action to the policy action space. And in the training phase, they add another set of trainable parameters called end of extraction. And the pointer network decoder treats this as one of the extraction candidates. So it naturally results in a stop action in the stochastic policy. And for any extraneous unwanted extraction step, the agents receive 0 reward. So they naturally stop extracting at some point. And again, repetition is always the problem that the summary systems have been encountering. And in order to solve that, they use some, the thing we just introduced in the last part, the last paper, the coverage mechanism, and also some other method called incorporate trigram avoidance that was introduced by Paulus in their paper in 2017. So actually this model, since it was trained with reinforcement learning, only performs well without these, but using the trigram method that was introduced by Paulus boosts the performance as well. So I'll just first introduce what is the trigram avoidance thing that was introduced by them. So this paper has the observation that in both the CNN and Daily Mail and New York Times datasets, the ground truth summaries almost never contain the same trigram twice. So they force their decoder to never output the same trigram more than once during the testing. And they do this by setting the probability of a particular trigram to 0 if that exact trigram was already existent in the previously decoded sequence of the current beam. So the paper uses this idea by they keep all k sentence candidates generated by beam search, where k is the size of the beam, and re-rank all k to the power n combinations of the n generated summary sentence beams. And in the end, they just re-rank the number of repeated n-grams, and the smaller is the better.
Wait, what about like stop words and stuff?
I think those are
Those are thrown away by the Rouge
Yeah.
metric.
Oh,
This mechanism you introduce is in practice quite efficient to increase your blue flow. I have seen in many papers the performance will significantly improve when they apply this technique.
the trigram thing, right?
Yeah, trigram penalty. Yeah, but some people believe that this is like a hack or trick.
Yeah.
So when you implement your own models, you should not use these to beat other baselines unless all the baselines use this. Yeah, about this mechanism, there are some critiques in the community.
Yeah, that's because of exactly as Taha introduced, that the particular data sets that they have,
Yeah.
scientists have basically observe this, empirical observation that trigrams are not repeated. Yeah. So you artificially induce that by putting this.
Yeah, it's basically a handcrafted feature.
Yeah.
So what does it improve the blue for?
I think because for sequence-based models, it is very common to generate repeated words.
Oh,
Yeah, but in your natural language, repeated words is quite rare. So when you use some rules to delete them, the performance will significantly improve.
What I think the previous paper, the coverage mechanism, was again a good idea. Do you think if that gives the same like performance?
Yeah. It's inspired by the same spirit.
Yeah.
Yeah.
But it's
They
quite
embody
automatic. Right?
differently. Yeah. I mean, a lot of this comes from the very even more early research pre deep neural networks. So there's in summarization, there's this famous heuristic called maximum marginal relevance, MMR, which says that you want to try to put in information that's somehow maximally different from what you already have in your summary, right? Otherwise, you keep on, especially multi-document summarization, where you have many articles that are talking about almost the same thing. Like, for example, you want to produce a multi-document summarization of like coronavirus, right? Then you're always going to get the same types of information because from a blue point of view or a rouge point of view, right? Rouge, basically, the evaluation for rouge just says that if you get parts of the gold standard summary right, you get points, right? But there's no inherent penalty for repeating things that are already in the gold standard. So if you say nothing but coronavirus 50 times, then you get perfect blue score, right? But you didn't say anything except for one word, just 50 times, right? So you need some way of reducing that redundancy, right? So all of these coverage mechanisms or marginal relevance is trying to do that, right? To say that whenever you add more space in your summary, you should be putting in something new to help somebody understand something more, right? And then when you do this you can think, all right, if you do it in a greedy manner, it's sort of like suboptimal, right? Because you're always picking what's the next best thing put in your summary, right? But it doesn't mean that your overall selection of things is best because you're being greedy, right? So you can also make this into our favorite NP complete choice problem, right? Which is to say you have this basket, right? You have to put in a maximum worthwhile items going on a shopping spree or whatever the analogy is, right?
Yeah, but I think still the coverage thing is not quite data dependent because if we train it on some summarization data that actually benefits from repetitions, that would still learn that, right? Although the trigram is quite handcrafted, it's like it doesn't let the repetitions to appear.
I mean, the best thing is if it's data driven, right? Because then as long as you have data, you can replicate the distribution in your target, right? But when you don't have that, then you can come back to tricks, right? I mean, when you don't have enough data, you engineer your features. I mean, that people have been doing that for decades, right? Lin did it in 1958. He didn't have any data. There's no such thing as supervised learning in 1958. And you created all the handcrafted features yourself and you ran your algorithm and you were happy that it actually ran on punch cards. Okay, so that's
Well, actually, the MMR thing kind of makes sense because when we are taught how to write summaries, it's also like every word is kind of like gold, right? You need to choose carefully the words that you.
yeah.
I
So
guess it makes sense.
yeah, so maximum marginal relevance is a greedy algorithm. It's sort of like k-means plus plus, if you know that algorithm, because I teach that in the machine learning class, right? When you do k-means, you're supposed to choose centroids, right? But you want to choose, when you initialize k-means, you want to choose centroids that are at least far enough away from each other. I mean, imagine if you start all of your k-means centroids at the exact same point. It's like really stupid, right? So you would at least try to separate them out, and that's exactly what we're trying to do here. Right? But you could get unoptimal clusters, right? You pick things too far away, then you pick outliers. I mean, why would you want an outlier sentence in your summary, right? It's not representative. Okay, so you want to throw that away too. So yeah, there's optimization problems in summarization for that.
Yeah. So that's actually all about the models. We didn't include the experimentation results because they obviously beat the state of the art, and that's why they are published. So the
Yes, like I say, for all of our reading groups, we never have to look at the main results because they're published works, so you don't need to look at. They're all sold up for the years that they came out, right? State of the art.
Yeah. So in the rest 10 minutes, I think it will even take shorter than that. We'll just like briefly explain two evaluation systems because it's one of the important areas in TS. So yeah, evaluation is actually quite a problematic aspect of automated text summarization. It's actually true in general NLP as well. So evaluating a summary is difficult because, as we just discussed in the beginning of the discussion, there is not an ideal summary for a given document or set of documents. And the agreement, even between human summarizers, is quite low, both for evaluating and generating summaries. And manual evaluation is too expensive. So the absence of a standard human or automatic evaluation metric is what's making it very hard to compare different systems and establish a baseline. But there are two very basic ideas that people have been using for the last 2 decades, I think. And one of them is Rouge. I mean, I've never had to pronounce it before, but I believe it's pronounced as Rouge. Right?
Yeah, it's a French word. Right?
Okay.
Yeah.
So yeah, formally it's just as Min already described in like 2 minutes ago, it's a n-gram recall between a candidate summary and a set of reference summaries. So what you do for to evaluate your summary is you basically count all of the n-grams that match between your summary and all of the reference summaries, and then just divide it by the number of n-grams that you have in the reference summaries. So it's basically a recall-based evaluation metric. And there's also another alternative to this that's looking for the longest common subsequence. And that's called RUGEL. And yeah, this is, as I said, it's a recall-based metric. Then we also have the below metric, which is a precision-based metric. But I'm just showing you the most simplistic versions of these algorithms because there are so many versions that people have been using. So what below does is the motivation behind the below, first of all, is that the text summarization systems can overgenerate sentences, as we discussed in all of the models that we have done so far. And so rather than counting every matching n-gram, a reference word should be considered exhausted after a matching candidate word is identified. And this is to actually solve the problem Min just pointed out. So basically, if you just create an n-gram that is favored by the reference word, then according to Rouge, your summary is a good one. But in below, you exhaust your reference matching n-gram when you use it once. So the algorithm in its simplest form looks like this. You first count the maximum number of times a word occurs in any single reference, and then clip the total count of each candidate word by its maximum reference count. And in the end, you just add these clipped counts up and divide it by the number of candidate words. So to just give you an example, if you like, let's say you have 2 reference words and one goes as the cat is on the mat, and the second is just the boy is running. And let's say your summary is the. So you have just like 7 Ds that are coming after each other. So according to Ruch, you have a good actually summary because your n-gram D matches all of the n-grams in the reference summary. Like if I'm doing a mistake, you can. But I think it was the. So I'm taking this example from the below, and that's what they were criticizing anyways. So what you do in the below is in the reference, you just first count the number of Ds, and so for the first sentence you have only 1 D, and for the second you also have 1 D. So then you go to your own summary and clip the number of Ds with the maximum number of Ds in your references. So in the end, you end up just getting 1 score for that word. And when you divide it by 7, the number of words in your summary, it just gets a score of 1/7. So below is much more informative in that sense. But both of these are being used in the area quite commonly. And as I already said, there are so many alternatives that people have been using that are alternatives of these very simple algorithms. But I hope this gives like some general understanding of how TS systems have been evaluated. And yeah, that's pretty much it. If you have any more questions or discussion points, we can go ahead and speak on that. That's all for us. Yeet, do you want to add anything, or are you okay?
Oh no.
Okay. No.
Okay, let's first give a hand to our presenters. Okay, do you guys have any questions? Okay, the evaluations measures that Taha and Yi presented are the most basic, right? They're basically looking at things as collection of words. That's it, or collections of sequences of words if you're thinking bigrams and trigrams. But of course, language doesn't actually work that way. Have the semantic analysis, clauses, etc. And we have to order this stuff appropriately, right? And like if you take a summary and you scramble it and you make it word salad, it gets the exact same, pretty much, rouge and blue if you look at just unigram, right? It's completely useless. So, you still have to think about other ways to evaluate. So there's a lot of other work in text generation and summarization that has to do with structuring the output, right? You want to make sure that your output is correctly ordered, right? You don't put the sentences or words in the wrong order, and that you capture coherent thoughts. So last week when we talked about RST and other discourse, right, we came across this idea of an elementary discourse unit, right? Basically a simple sentence or clause, right? So you can do that with summarization too. You can compute something like blue, not over words, but over clauses. You can say how many key concepts or key things that you get in your summary. Okay? And that system is called pyramid. That's another metric that you'll see. Okay, pyramid basically says there's a tree of important information in the source document, and you want to see how many branches of that tree are represented in your target summary. All right. Hopefully they're in the same order, so you can reproduce like a bonsai version of your tree. Does that make sense? Okay. So we talked about that last week in RST. We said if you want to summarize an RST tree, you just cut off as many leaves as possible and leave the branches, right? And then you've got an RST summary, right? Because the nucleus of the argument is at the top of the RST tree. Okay.
But,
So,
for abstractive summarization, right, the goal and the metrics don't match at all. Like you want to produce new words, but you're using the source sentence to compare and graph. Like you want it to be as abstractive as possible, but
Yeah.
you're using matching and that somehow doesn't make any sense.
Yeah, so this is why extractive summarization was pursued for such a long time, because it was easy to judge, right? You can always make abstractive summarization as a sentence selection problem, okay? I have k sentences in a document, I select n much smaller than k. End of story. That's the problem with text summarization. When it's abstracted, you have to deal with what Taha calls, and the paper does call too, out of vocabulary. Things that are not in the document that you have hallucinated should be there, right? So then you have to judge that. That becomes difficult. That's why data-driven approaches to abstractive summarization have only recently come up. Because there's no corpus to support it. There's no statistics to support that, right? You'd have to go back and say, if I have no label data, you would do what Lynn did. You just come up with a bunch of metrics and then say, okay, do your best. Maybe you put them into a linear combination like the Kupiec paper, which was from Xerox PARC in 1995, right? You guys went over that, and just do that, right? Okay. But you can imagine when Taha went over the very beginning and said, actually, we need to know what summarization means. Actually, we haven't really scratched that topic at all, right? All the algorithms that are presenting here are saying that you want to present the version of the summary, but in shorter words, okay? But it doesn't address query-focused summarization. It doesn't address summarization for different audiences, okay? It doesn't address difference between indicative and informative summarization. All the summaries that are created right now are basically targeting informative summaries because they're trying to take the whole document and compress it, like gzip, right? If you're giving gzip as a compression, as a summarization algorithm, it's pretty good, right? It's not lossy. It's just not readable anymore, okay? But it's a compression algorithm, right? So if you want to compute something else, like an indicative document, it says, just show me the important parts, make a judgment call on your own about which things are important, which things are not, throw out the ones that are important. Don't even try to put them in the summary, okay? That would be a different loss function. Okay? So I think those are all worthwhile things for you to think about contextually. And then, because text summarization right now is still very simplistic, okay? It is a good area still to work on, okay? And the person who started this work was actually my advisor. So my advisor, Kathy McEwen, when she wrote the first text summarization paper, she also wrote the first book on text generation. So both of those application areas came from her in the 1970s. So yeah, it's a long time ago. Yeah. Okay. So I think we're just on time. It's 2:59:55, so we'll end there. Okay. Thanks, everyone.